a request for the Zoom participants and for the in-person participants. So the more questions, the better. So last time we've finished with the definition, actually, so of a vertex separated algebra. And actually, let me start with the variant of the definition, which is going to be important for us. And well, almost all the examples we are going to study will be of this form. So we define a graded vertex separated algebra as follows. So we have a vector space V, the direct sum of Vn, and being an integer, and the vacuum vector sits in V0, like this. And so, as usual, I mean, as in the general situation, we have Y, which is a map from V to end V Z, Z inverse. So the images Y of AZ, so these are fields. And so the convention is that we are writing them in the following form. So A lower n in brackets, they are operators on V. And so we assume that the conformal dimension of Y of AZ equals M for A in Vm. Okay. So once again, so for any vector, we have a field, and well, we have a notion of the degree of a vector, and we have a notion of a conformal dimension of a field. So let's see how does it work. So we can write Y of AZ as the sum of Z to the n, A minus n minus 1. Okay, so just rewrote the definition. And then the condition on the conformal dimension means that the degree of A minus n minus 1 is equal to what? Do you remember the definition of the conformal dimension? So we have this conformal dimension M, and then we also need to subtract this number, to add this number. So it's M plus N. So let me check if I wrote this in the same way last time. Let's see. Yes. Not necessarily. So yeah. So this is the notion of a graded vertex separated algebra, and here we do have such a condition. So this equivalent to saying that the degree of an is M minus n minus. Okay. So in particular, so for example, if m is 1, then the degree of an is minus. Just to have a feeling how it works. So it means that if you take a vector from the first graded component, then the degree of the corresponding component an is exactly minus. Otherwise, we are getting some shift. Okay, now, yeah, and of course, so the usual definitions of the vertex algebra do apply here. So the most important thing is that all fields y, a, z are pairwise local. So this is the condition, and we also have conditions on y apply to the vacuum, and so on. Yeah. So the all other axioms of vertex utility algebra they do hold here as well. So the most important difference is that we have this grading, and the conformal dimension of the fields is prescribed by the graded component of the vector. Okay. So now let me also give a few general notions, which are rather standard. So for example, let us define what is the homomorphism of vertex utility algebras. So can you guess what this should be? Right. So this is the map from the vector between the vector spaces. Yeah. So phi from say V to V prime, where V and V prime are vertex utility algebras. And what are the conditions we want to satisfy? Yes. Indeed. Yes. 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 Yeah. Actually, this is the only thing one can guess or invent or whatever. But actually, there is one more minor condition. So what should it be? So we have one more important ingredient of vertex utility algebra. Say it again. Even more basic. So there is one. Yes. 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 This is important. Let me write it here. So phi of 0. Phi of one vacuum should be another vacuum, and this is important. Okay. So this is a homomorphism. And now one more also very standard thing is vertex utility algebras, subalgebras.
I'm sorry, do we not need a condition for T?
So the condition for T, I think it should follow maybe, but anyway, you're right. So let's say that we apply T and then phi, the same as phi and T prime. Okay. And what is a vertex utility algebra, subalgebra? Yes, so we have vector spaces embedded. So with what condition? Well, you can put it like that, but if we just say that some subspace is a vertex separated algebra subalgebra, how can we say it? Well, I mean, we just have a subspace. How to understand that this subspace is a subalgebra? We don't have a subalgebra yet. Yes, just a subspace. Yes, but how? I mean, so I mean, this is, we have a structure of Y here on V. Yes. Yes. So actually, the only condition is that if we take two vectors A and B from V prime, then this sits in V prime of ZZE, right? Just the condition is that the iteration does not somehow leave the vector, the space V prime, right? So it's related. And maybe the last general thing to say is a vertex separated algebra ideal. So what is that? Mm-hmm. Uh-huh. Mm-hmm. Like this, right? Yeah. Yeah. That's a good point. So actually, so this should be seen like a left ideal, right? And we can do vice versa, taking any A and I and B and B and asking for Y of AZ, Y to B in I of Z plus minus 1. So this is a kind of right ideal. But actually, we are not going to prove it right now, but the following remark is in order. So all ideals in a vertex separated algebra are two-sided. Well, this is a property, but we're not going to prove it right now, but anyway. Okay, so now, so any questions about general definitions, notations, and so on? Sunday, how many people are in Zoom? Good. So these are the ideals. And now let me get back to the example we've seen last time before going back to the kind of general construction. So example is the Heisenberg vertex separated algebra. And what's that? So recall that we've seen it last time. So our V is pi. So this is the POC module for the Heisenberg algebra, and this is graded. So in particular, so pi is actually isomorphic to or equal even h minus 1, h minus 2, and so on applied to the vacuum where vacuum vector spans pi 0, the zeroth graded component. Well, we need to define our operation. And we've seen that this is just h of z, hn z minus n minus 1. So this is just the definition. Once again, I mentioned it last time. Please note that this hn here is not just a Heisenberg algebra element, but an operator acting on a Fock module, like this. Okay, and now this is our hn. Now, how do we proceed? We want to define other vectors, for example, y of h minus 2 z. And well, what should be the conformal dimension of h minus 2? So we want a graded vertex separated algebra, and so we have the condition on the conformal dimension. So what should it be? Well, I mean, we have a field which corresponds to such a vector. So what should be its conformal dimension? But why are you thinking that hard? So we have this definition. What is M? What is M? True. Yeah. No, wait. So let's just read this line. Yeah. So do you know some? So, and by the way, what is the conformal dimension of this guy? It's 1. And indeed, you see, so you see this, for example, there, saying that if we take m equals 1, so a vector from V1, so then the degree of an should be exactly minus n. And this is how it works here, yeah. So this is actually this h lower n is h lower n bracketed, yeah, and the degree is exactly minus n. So it works. But do you know some way how to increase the conformal dimension? Some natural way. So having a field, how can we get? No, yeah, the derivative makes the conformal dimension larger. And actually, the integration is a kind of little bit delicate operation. Yeah, but the derivative is fine, and let's just write it. Okay, so, and there is one more thing, one more vector on the second layer. So it's y of h minus 1 squared applied to the vacuum. Well, so far I'm just defining this. Yeah, I'm just defining. I'm trying to kind of motivate the formula I'm going to write, the general formula, but this is the way how you can guess so what it should be. So any guess for this? So is there another way to somehow make conformal dimension 2 out of the conformal dimension 1? What you can do with a field to make conformal dimension 2 out of 1? So maybe somebody in Zoom can tell us.
Divided by z.
By the way, in the audience, in Zoom, can you say something in order to check if we can hear you?
Здравствуйте.
Hello? No? Oh. Yeah, it seems we can't hear people in Zoom. Yes, yes. So this is a good guess. But is it a well-defined thing? No? Why? What's the problem? Yeah, so in principle, if we write it like that, so this is the sum over k, z to the k, and here we put the sum hi, hj, I plus j being k, right? So by definition, this is this expression. But now the point is if the sum is a well-defined operator or not. And actually, the point is it is not well-defined. Yeah, but this is not real. Well, the problem is actually very minor. So, for example, you see if we have, say, the sum I plus j equals, say, 5, hi hj. So does it make sense? So I just want to state that of course, so this is an infinite sum, but I'm saying that it can be applied to any vector, giving only finite number of non-trivial terms. So can you explain why?
Sorry, из Zoom слышно что-то сейчас?
Right.
Нас слышно?
Mm-hmm. Right, right. So the important thing is that so if I plus j is non-zero, then hi j equals aj hi, right? And therefore, actually, for any for a v, say from phi s, hi hjv is 0 if I is greater than s or j is greater than. Yes, because hi and the j, then they somehow make the degree smaller, and well, they subtract I from the degree, and therefore they're only finally many terms acting on 3D. However, so suppose we have the sum I plus j equals 0. So does it work fine? Is it well defined? They don't. But still, so I mean, so is such a sum well defined as an operator on the Fock module? Yes, but so you see there we also have sum of infinite number of numbers. However, by some reason, turns out to be only finite sum. So can we check if a real problem occurs here?
А сейчас слышно?
Yes, but maybe these numbers are 0, starting from some point, or they somehow converge or whatever. Yes. Let's try to apply it to some vector and check. Very good. Yeah. Yes. Yes. So what is this? Well, cx by 1. Like this, right? And it clearly does not produce anything meaningful, right? So this is the problem, and in order to avoid this, so we introduce something which is called normal ordering. So this means that this is no good. But in order to make it somehow nicer, we can write y of h minus 1 squared 0 z. We can define it as h of z. These two dots on the left, on the right, this is the normal ordering. And the definition is that we say that hk, hl equals to hl, hk if k is positive, or hk, hl otherwise.
Zoom не слышно, да?
Oh, we can hear you now. We can.
Good. Thanks.
Yes. Very good. So any questions from the audience, from the Zoom audience? So maybe somebody can say something, not Pasha. Just to understand that we have a connection with the Zoom audience.
Нас слышно?
Yes, yes, now we can hear you. Okay, so the goal is somehow to put the positive guys to the right, so they can act. So in particular, then the sum hj, h minus j is always so for equals to h minus j, hj for positive j. And then such problem as we've seen there does not occur. Okay, so now let me formulate the general theorem. So saying that the formula y of h minus I1 minus ik0 of z is 1 minus 1 over I1 minus 1 factorial ik minus 1 factorial times z I1 minus 1 h of z times dz ik minus 1 h of z produces the structure of a vertex separated algebra on phi. Okay. So this is the formula. Well, so we have several fields here. All fields are derivatives of the initial field h of z, and then we take the product, but then the normal ordering is easy. We say that A, B, C is A, B, C. So I think here it does not make any difference. So here, yes, but in general, so we'll give a general definition in several minutes, and then this general definition is not commutative, and we always assume such a convention. Okay, so we are not going to prove this theorem right now. So in principle, you can try doing by hand, just by brute force computation, but it's rather complicated. So the main problem is to show that the fields are pairwise local. Yeah, so it's really something to do. So not too complicated, but still. But we will prove the general statement, so which will allow to somehow proving such theorems in our general pattern. Okay, good. Now, so as I said, this normal ordering is somehow important for the definitions for kind of in order to define vertex separated algebras. And let us give the general formula, the general formula for this normal ordering, because you see here these fields or these elements, they satisfy very simple commutation relations, and therefore the only thing we have to do is just to kind of change the order. But in general, the commutation relations are much more complicated, so we need more work to do. So let's first of all, notation. So we have f of z, which is the sum fn z to the n, n from z. We say that f of z plus the sum n greater than 0, fn z to the n, and f of z minus the sum n less than 0, fn z to the n. Yes, so just kind of splitting the whole sum into two pieces. And now we consider the field, say A of z, which is the sum an z to minus n minus 1. So let me give an example. Then can you say me what is A of z plus? Say it again? Yes. And A of z minus so let me check if everything is compatible. Yes. Okay. So now let us give a definition. So given two fields, A of z and B of w, so we define this as A of z plus B of w plus B of w A of z. So you see what we are doing, we are somehow splitting a field A, which is on the left, into two parts, A of z plus and A of z minus, and then we somehow move one part to the right. And you see this part corresponds to the operators having here non-negative coefficient. Okay. Good. So this is our definition, and now so you see this is in fact absolutely the same thing we did with the Heisenberg operators. Namely, for the Heisenberg operators, we just move the positive to the right, and actually this is what we're doing here. So any questions? Yeah, so the most important property is that so I'll write it right now, but we can write A of z, B of z. So this product does make sense. So we'll show it in a minute, but this is kind of the most important thing. Okay, so let us formulate the following theorem or proposition. So the proposition is as follows. So there are several statements about this normal ordering. So the first thing is that if you take phi from B star, V from V, then we can take the matrix coefficient just apply it to V, and the result is in Q of ZW applied to the inverse, multiplied by the inverse W. Yeah, so just want to say that the result of such an action somehow belongs to this rather small thing. And then the second part is that if the B of W is well defined at T equals W. Okay, so there are probably a couple of more properties, but maybe let me somehow skip it until the next thing. So how to prove it? The proof works in a rather straightforward way. So if we have A of Z, B of W, and apply to V, by the very definition, this is equal to A of Z plus B of W applied to V plus B of W, A of Z minus applied to V. Now, can you tell me where does this guy sit? Yes, for example, where does this guy belong to? Right. Yes. Yes. Just since these are fields, so this sits in V of Z, right? Right. And now, if we apply this sits in where? So these are only non-negative powers, yes, of Z. We have plus here. Okay. So we have ZW and only finitely many negative terms, right? Okay. Does this make sense? Okay. And now let's move on here. So where does this guy belong to? A is a field. Yes.
Полиномы от z-1 над v.
So this sits in V of Z inverse, right? And the total thing belongs to V of Z of W. Yeah, this is a very kind of up-to-date comment. Yeah. Okay. So if we sum up, then this guy sits in V of VW of the inverse W. Okay. So this part A. Now what about part B? So by definition, if we take like this, so we take A of Z plus B of W.
Поверните камеру, пожалуйста.
Sorry? Some question? Plus B of W, A of Z minus. And we put W equals Z. Then the result is the sum AN BM Z to minus N minus 1 minus M minus 1. And here we should put N negative, right? Plus BM AN V minus N minus 1 minus M minus. Did I write it correctly? So actually remember, maybe we still have it somewhere on the board. Yes, right here. So you see we have this formula for A of Z plus and A of Z minus. And I just rewrote it here. Yes, let me show you the reason. Actually, we have it here. So let's see this formula. So this operator Hn, yes, which is written here. So this is the operator which has conformal dimension 1. Correct? Just since the definition actually, so this is the equation where we start from. So we said that if we write sum AN Z to the minus N, yes, then the conformal dimension is something like delta minus 10. Yeah, something like this. But then we've seen that the conformal dimension of this field, written in such a way, is exactly 1. And so this is the reason. So if you want the conformal dimension to coincide with the component where the vector sits, then we are forced to write in such a way. And since this vertex operator algebra business comes from physics, and the main objects for physicists are fields, so not the vectors, but fields. So the vectors are kind of convenient algebraic way to work with these fields, to organize them, but in principle the fields are the main players. Then the conformal dimension of a field is something God given. And then when you somehow write this Fourier decomposition, then you try to somehow follow this path. Okay. Very good. So then we can just collect the terms k from z, and we write here z to the k, and here the sum n less than 0. Let me maybe write it minus k minus 2, and here n plus m is k, a n b m plus the sum n greater than 0, n plus m is k, b m a. Okay. Well, and then clearly this sum is well defined. So I mean, if we apply, so for any v from v, only finitely many terms contribute non-trivial. Absolutely. So here they are positive, and the sum, well, just positive. So they're only finitely many here, and here this can be negative in principle, but yeah, there are only finitely many negative terms here. Yeah, because n is strictly less than 0, and n plus m should sum up to something fixed. Okay. And actually, this is the most important thing. Okay. So this is the first part, and then let me add one more lemma. Actually, saying how to compute this normal ordering. So any questions about this computation? So other questions from the Zoom audience? No questions. Okay. Good. So let us do the following. So maybe before stating the lemma, let me recall that we have delta z minus w, which is the sum z to the s, w minus s minus 1. And this can be decomposed into delta z minus w plus z minus w minus, where, for example, z minus w plus is as usual the sum s greater or equal than 0, like this. Again, let me check if it works. Yep. Sure. Yes, it is. Yes, this has to be checked. Let's see. So suppose we apply the sum to some vector v, and v is, for example, homogeneous vector of some degree. So then let's see what are the cases which somehow have a chance to act non-trivially on this vector. So let's see here. So since n plus m is k, and there are only finitely many terms acting non-trivially, and so for okay, let me say it like this. So suppose k is very large. Yes. So if k is very large, then what do we have? So we start with an, and the n is greater or equal than 0. Therefore, m should be k minus n. So m is less than k. Okay, less or equal than k. But this an makes the degree of a vector smaller because n is greater or equal than 0. So therefore, there are only finitely many k such that this sum can act non-trivially on V. Because B is a field. And similarly, here, since A is a field, yes, here M is K minus N. So it's greater or equal than K. Okay, then the degree of BM applied to a vector, so maybe we should write it at some point, but this somehow combination of the fact that A is a field and B. Okay. And the lemma, which is somehow convenient for computation, says that the value at z equals w is equal to the residue at z equals 0 of the following things. So we take delta of a of z w plus delta of z minus w minus d of w is so is it clear what's written here? Maybe I should switch the minus here and plus here. So the residue is the coefficient in front of the inverse. Okay. Z inverse. So we take the residue at z equals 0. Well, this is written as z. Well, I didn't have to say it. Z equals w, right, as series in W. Okay. So of course I can rewrite it as a series in V, but right. Okay. So how should we do it? Well, just let's write the first term. So delta minus B of W, with the residue at 0, equals to in sum Z to the S, W minus S minus 1, and S is less than 0. And then we take the sum and M, AN, BM, Z minus N minus 1, W minus M minus 1. Okay. So if we sum up, we have the terms Z here and here. And so the residue comes from S equals N. And the S is negative. So we get the sum N less than 0. Yeah, should I do it this way? Yes. N less than 0, AN, BM, and M arbitrary. And here I take Z to the minus N minus 1 and W yeah, so no Z, of course. So W minus M minus 1, and then minus N minus 1. So is it what we want? Yes. And we want this to be A of Z plus B of W. Is it true? Just by definition, right? So here we have the sum of the degrees, and here we take N less than 0. And this corresponds to A of W, B of W. Okay. Good. So, and similarly for the second sum. Okay. Good. So the last general remark I want to add here says that so if delta 1 is the conformal dimension of A of Z, and delta 2 is the conformal dimension of B of Z, then A of W B of W is of conformal dimension. What? Well, simply because we have products in our formula, and the degree of a product is the sum of the degrees. Okay, and the deltas, they enter linearly. Okay. So any questions? Um, yes. So I mean the residue is an integral of the product over the circle. Yeah, you can put it like that. Yeah. Algebraically, this is the most clean way to formulate it, but of course you can use the integral. Okay. Good. So yes, maybe that's all I want to say here. Yeah, one more. Let me say one more time. So we always, in what follows, we always assume that A, B, C is A, B, C, and so on. So this operation is non-commutative. Okay, so in order to somehow check, for example, that the yeah, maybe one more remark is that so the definition of the normal ordering for the Heisenberg algebra agrees with the general definition. Okay. Good. So you remember that in this explicit formula we had for the Heisenberg algebra, vertex rate algebra, we had normal orderings of products of several derivatives. Yes. So and the main task in order to prove that something is a vertex separated algebra is to prove the locality, so that the fields are mutually local. So if we start with some basic fields, say h of z or derivative of h of z, and assume we know that they are local, then we need some tool in order to prove that the products, the normal ordered products, are also pairwise local. So for that, we need the one technical statement, which is called the Dong's lemma. Saying that let A of Z Dong be mutually local fields. Then C of Z and A of Z, B of Z are also local. Okay. So the lemma says that if you can check the locality of three fields, then if you organize a normal ordering out of two of them, normal ordered product out of two of them, then what you get is again the two new fields are again local. And how to prove this? I don't know if we have enough time. Okay, let me start and then we'll see. So we know that there exists a number R such that for any S greater than R, not greater or equal to R, the following holds: Z minus W to the S A of Z B of W is Z minus W to the S B of W A of Z, and Z minus U to the S A of Z C of U is Z minus W to the S C of U A of Z, and U minus W to the S C of U B of W equals to U minus W to the S C of U B of W. Okay. So we claim that we take n equals 3R and claim that Z minus, how should I put it? W minus U. A of W, B of W, C of U equals to C of U, A of W, B of W. Okay. So this is what we actually need to prove, right? And you remember we have the formula, which might be still here. Yes. Oh, no, it's gone. It's a pity. Sorry for with the residues. Here's the formula. So this is the formula we need. And so you see, we know that this normal ordering is such a sum of residues. Okay, actually the residue of the sum. And therefore, if we prove that after substituting the in bracket expression instead of this normal ordering, we get the correct formula, then we are done. Okay, so I just want to, instead of writing this, I want to say that this is implied by saying that w minus u to the n, and here we put w plus LD Q equals to, and here like. So if we are able to prove this equality, then we are done. Okay. Good. So so the idea is to write this minus u to the n as w minus u to the r times w minus u to 2r. And this is expressed as the sum as from 0 to 2r, double binomial coefficient. Here w minus z to the s, z minus u to the 2r. Okay. So we have this guy, which stays here and here. And then we want to understand, to prove this equality. And for that, we write such a product, and then we such a power as such a sum. And then we need to prove that actually this is true. So maybe I just leave it for you for the homework as a computation. Actually, there is more or less nothing to say. Or so what would you prefer actually, since you are in the audience? So shall we complete it, or you want to spend some time at home completing it? Let's vote. Flower. Okay, I see Andrei. Okay, Dina. Okay, good. So then we leave it for as a homework, and maybe the last thing to okay, maybe just stop now, and then I ask if you have any questions or further comments, remarks. So. well, you have two fields, and then you produce. Yeah, maybe I should add this. Yeah, so maybe complete the proof. Homework. And remark, which actually Andrei said, that if A of z, B of z are fields, then the normal ordered product is a field as well. And actually, this is not, well, so it's also an easy exercise, but you better realize. So further questions, remark, comments? Well, I mean, you will see that there is something called the reconstruction theorem, saying that you can reconstruct how to say? Let me postpone the answer until the next lecture, but in principle, yes. So you're right. There is a vector such that the normal ordering corresponds to some vector, but you can say explicitly what the vector. Yes. Yeah. So it corresponds to applying some Fourier component corresponding to one field to another. So further questions? Okay, so if not, let's stop for today and see you next time.
Спасибо, что